Let's go over chapter 7 for threaded fastening. So let's start. We're given this part A. We need to be able to find out typical uses, machine and control of threads, the standards and definitions, stress calculations, threaded fasteners, and good practices. And before we do any of this, we need to first be able to draw this. So what I'm going to do here is put this here like we did earlier in the previous video. Let me just turn this off. Okay, we're going to first draw this ourselves. Okay, so what's here is first you have a center line. So let's draw this. First you have a center line. So I'm gonna cheat here. I'm just gonna cover here and then just get rid of this. Okay, yeah, that did not work. You know what? Make my life easier. So this. We got our center line. Okay. Now, after the center line, we have to draw. So first, let's draw this base over here. So let's draw this base over here. And with this, you have to draw something like this, going down. Now you want to make sure this distance the same, this distance also the same. So then from here we draw a line across, an inward. Obviously my drawing is really good because I'm just using an online software, but in reality we have to make it more like what we want. So after this we need to draw from here. So from here, maybe a bit more accurate, symmetrical on both sides. Okay. Then we draw a line across. And from those lines we drew earlier, the diagonal lines, just draw it till here. And again, draw it till here. Okay. Now we draw upwards to, let's say, over here, upwards to here, upwards to here, upwards to here. Okay, then we just draw a line across here, a line across here, not like that, a line across here. Okay, yeah, let's move it down. Alright, cool. Then from here to here as well. Okay, and then we just join these points up. So here to here and here to here. So this is our bolt. Okay, so this is something that we need to be able to draw. Okay, so let's go back here and to our lecture here that we're trying to. Okay, so threading fastening. So this is just a quick drawing of what we need to draw. Let's go to part A and see what we have over here. So the fundamental operation in this creation of shape, this includes assembly where a number of components are fastened and joined together permanently by welding or detachably by screws and so on. Fasteners based upon screw threads are most common, so it is important that their performance is understood and the limits are appreciated. Okay, is there anything here that we need to write on? So fundamental operation is in manufacture is the creation of shape. This includes assembly where a number of components are fastened or joined together permanently by welding. Either by permanent welding, for example, or detachable by screws, nuts. So this is the threaded fasteners. Okay, so the importance of fasteners. So let's just have a quick thing here. Okay, text, importance of fastening. So obviously we do not want header. Let's do body. Control B, importance of fastening, and Control B out. Okay, so 50% of production is spent on fastening. Maybe I'll just increase the size here so it fits. Yeah, okay. Then they're critical to product performance. So fasteners are important for product performance and reliability. Okay. Let me capitalize this. So, count fasteners. All right, let's go back down again. Okay. Choosing as part, so product design. So, product design. Choose. All right. Okay, let's go back over there. Choose proper fasteners. Okay. Common failure modes. So you got over tightening, corrosion, fatigue. So this might be asked. So let's quickly just write it over here. So we got failure. Actually, let's do failure in red. Bold. And let's write failure. Oh no. Let's change the color to red. Failure modes. Okay, and we're going to revert to purple. There we go. 40% for over tightening. Okay, let's just add. Okay, cool. Over tightening, 30% corrosion, 20% fatigue, 10% misalignment. Okay, anything else you need to know from this? So can lead to thread strippage or bolt breakage. Weakens fastener over time, particularly in harsh environments. Repeated load cycle can gradually weaken fasteners. Improperly aligned joints, increase stress and potential failure. So with this, what I didn't know was that I didn't know that can lead to thread stripping or bolt breakage. So actually, let's gonna just emphasize this here. So this part here we have bolt breakage, harsh environment, and fatigue is just repeated load cycles. So repeated cycles. Okay, misalignment, improperly aligned joints increase stress. So let's just stress increase. And yeah, okay. Next one, we got typical uses. Now we're at the use. So it's used for 7 different components. Assembly of pipes, helical guiding from. So okay, this looks important. So we can use it for. Oh, this looks something that can easily come in the midterm. So we're probably given this, and then we might be asked for the kinematic diagram for this. So that just a note. So just remember that. We might be asked about that. Okay, so if that's the case, let's go up here and if we can try to just put them in one sentence, that'd be great. So let's put it here. And oh wait, no, I want to text here. So let's start from here. Okay, I'm going to do some blue. So uses. All right, so we have assembling. Oh no, let's use a different color. Uses orange. No, orange. Yeah. Assembling different components. assembling of, why can't I, hold on, okay, assembling of different components, pipes, and this is to prevent leakage. Okay, so that's all right, prevent leakage. What else? We have helical guiding. Hold on. We have helical guiding, and this is, it transforms the rotation translation. So rotation into translation. I'm going to put a box around it in a minute. Hold on. Another thing, we can use it for material transportation. So material transportation, aka water up a well. Okay, cool. Now I'm gonna just, if I can maybe make this into red. There we go. Here we go. So this is important because this is the only one that can rotation into translation. So I can't spell. So it's transportation. What's this issue here? Okay, did I underline this? No, it just, okay. Okay, we're just gonna ignore it. Okay, cool. Now part B, machining and control of threads. So we have manual machining, which we did in the workshop. We use taps and tap handles. So now we're at part B. So now let's quickly write part B here. So part B, change this to this one, and change this to this one, and let's bring it down here. Okay, maybe actually let's increase the font size actually. Oh, okay, part B. Alright, cool. Now we're at machining and control of threads. Cool. Okay, there we go. Now this is important, taps and handles. So this is, now we're going to do the manual machining of internal threads. So, okay, let's do here. Body, okay, manual machining of internal threads involves taps plus tap handle. Okay, before we continue, let me just bring this here. This is our taps and tap handle. Okay. Alright, cool. Now let's change the color. So we have 3 stages here. So we have one. And what we do is, this is the taper tap. Then we have your intermediate tap, or second tap. And then you have your bottom tap or finisher tap. I'm gonna call it finisher tap or bottom tap. Oh, sorry, finisher tap, bottom tap. Here you go. Bottom, and second is also called intermediate. So intermediate. Now what's happening in all this? So in this you have this is just the initial start to start the tapping process for a female thread. Okay. They have a long head, so you can see here it's not as smooth. This is just the first tap. Okay. Then from there it gets more smoother as we go across. So the second tap is just, you're adding more holes, and then at the very end, this is where you have, it's very, so if you look here, the holes at the top is only in the beginning. Then we're adding more, and we're taking more chunks away from the material, and then at the end we have the bottom tap. This is at the end. So this is just start, let's say maybe taper tap first half. Okay, first half of the thread. Then this is maybe like 70%. 10%. That's 70% of the threading. And this is your final says finishing the bottom. Okay. All right. So yeah, I mean that makes sense. I don't think we need the images. I mean we can put the images just for reference. I don't think we need any more than this because I think we did a physical thing, so we have an idea. Okay, let's spread them side by side. Second tab. All right, let's spread second tab, and I think we'll have enough space for the third tab. We'll make space. Let's close the sound here. All right, this is our bottom tab. All right, cool. Okay. Then we have your manual machining of external threads. So we have die plus die handle, and we just do the same thing but for external, and we add lubrication. So I'll add here that you have your let's change the color to green. So now we have manual machining of external threads, and this is when you have die plus die handle for both right here. For both, lubrication is required. Okay, because that just makes the process much more faster to avoid any friction. Okay, there's this G code. We did this before in manufacturing processes. So high series industrial roll machining. So they use the rolling mechanism to thread large beams. Okay, so they use a short tool changing times, high precision guarantee of smooth cutting, very good surface finish, and high tool life per edge due to even cutting action. Okay, so I think that I mean that's pretty straightforward to be honest. But we'll just make a note of it. So we have your high series. This is industrial machining. Pros are short tool changing times, high precision. Actually, no, I'll just get rid of this. High precision. Okay. A good surface finish. Or, yeah, great surface finish. Here we go. English. Finish. And high tool life per edge due to even cutting action. So what I'm guessing they're saying because this is a machine, they have very high tool life even to the very edge. Okay, due to even cutting action from the machine. Okay, now we're just gonna change the font color of this to black, and we're going to change this to blue. Hold it. There we go. Okay, this machine. Then we're just gonna have a quick image of our thread whirling tool. Okay, cool. Why is the let's put it here. Cool. Let's turn it off. How can we control these threads? How can we control them, or how can we check the measure of this? We can use a thread gauge or a vernier caliper. So to measure the threads, thread gauge, vernier caliper. Okay, and again. Okay, and we're just gonna quickly. All right, cool. Thread gauge. This is our thread gauge here. So thread gauge, so thread gauge here, and the vernier caliper. So quick summary here. Okay, cool. This is our vernier caliper. Now, part C, this is the thread standard and definitions. So let's try part C here. So let's have a part C right about here. Format header 2. Part C. And let's format this header 2. And there we go. Part C. Ooh. That's right here. Standards plus definitions. Alright, cool. So we have bolts versus screws. So what are bolts versus screws? So a bolt is designed to pass through a hole. So this again, very important. We need to know these definitions and the differences between them. So let's change our body. Let's change this to, not this. Let's do it in a different color. Let's do it in no, I mean, no, that don't look good. No. Okay, there we go. Bolt is done to pass through holes in meeting members. So pass through holes in meeting members and secure with a nut. With nut from opposite end. Okay. Screw, however, is designed to pass through holes in one member to be joined in a threaded hole in meeting member. So difference is one member versus meeting members, secured with a nut and secured with the is joined to the threaded hole in the meeting member. Alright, so that's important. Alright, cool. So I'm gonna have a quick bolt versus a bolt. So let's bring that here. I also don't like the color of this, so just quickly change this to, so there we go. Okay, and then screw. This is our screw here. And this is our screw here. There we go. Okay. A screw is an inclined plane wrapped around a shaft or cylinder. The inclined plane allows the screw to move itself when rotated. I'm just going to add on to this. So we're just going to write that it's an inclined plane wrapped around a shaft or a cylinder. Right, cool. I'll do this in green like they've done. Okay, the plane allows the screw to move. So let's mention here. This inclined plane allows the screw to move itself when rotated. I think if I just do this, yeah, there we go. Okay. Geometric features. So we have pitch, the distance between adjacent threads. So this is between adjacent threads. If you zoom in, adjacent threads. Okay. Major diameter, largest diameter of the thread. Okay, got it. Minor diameter is between the smallest diameter of the thread. So we're talking about this one here. It's the very smallest. Here. It's here to here. That's the minor. And then the mean is them added was when you have, oh, it's not given here, but okay. Pitch diameter is theoretical diameter between the major and the minor. Okay, and again, is that the mean as well? Okay, but these are just geometric features, so I don't think we will be asked about like labeling them. To be honest, I don't think that's the issue. But if that's the case, we can just have a big picture here, so we can just look at what we need here. So I'll just have a picture here. This is for threads. Okay. So minor diameter, pitch diameter. Yeah, so that's some the mean diameter is the pitch diameter then, yeah? Yeah, okay. The theoretical diameter, okay. Okay, P crest root, yeah, okay. This is how we represent threads, external threads in our drawing. So let's quickly do that here. So black. So we have here, this is your center line. And then from there you have a circle. You have a circle. Okay, we have circle. And in that circle, we have a 3/4 of a circle. So let's draw on the circle. Okay, and then in this, let's do partial. So this is not there. This is for external threads. Okay, I'm gonna just hold on. Make a small one. Okay, let's go to white. So this is our section, so our center line. Alright, so this is how we show the external thread. So this is external threads from the end. So this is end view. And then we're going to have internal threads as well. So the only difference is, look, it's enclosed. So we're just going to take the same drawing. We're going to duplicate it because it saves us time as well. Control C, Control V. Sure, let's go with that. I just need this part here. Okay, I'm gonna just do this. Yeah, here we go. Okay. And instead of having external, I'm gonna just write internal. Okay, hold on. Alright. Internal threads. That works. So internal threads. And then this is just in a box. Yep, okay. End view. Okay, so external, internal, so the same thing here. So look, if you look in detail, this is for external threads. So you have the same drawing as, so you have your crest and roots, and you draw them together. And then for internal, you do the same thing, you just draw a box around it. That's it, same thing, just draw a box around it. And this is shows that it's internally threads. Okay, so this is how we show it. Okay, another view that we should show it is this one over here, the side view. So I'll also actually no, I won't draw it. I'm just going to copy it so it's easier. I drew this one because I think this will probably be asked, so that's why. Okay, there we go. Now we have geometric features. When a nut on a screw is rotated by one turn, it travels along a distance of lead L. So this is our L here. L. Developing one turn of thread, the mean diameter, the average, major, and minor diameter give the lead angle, and it keeps on going. Now, what's important here is to note that if you have single start, L equals your pitch. This is just your, hold on, go back here. Your pitch, yeah, just your pitch. Distance between adjacent threads, yes. If you have a double start, it's equal to 2p. And if it's triple start, it's equal to 3p. Now more than this is not possisible. That's what the professor told us as well. Yeah, there you go. Leads, not possible more than this. Alright, cool. So what we can do here is, this is a really good diagram here, but we don't want to copy everything. So, or at least the space, we want to keep the space. So we're gonna have LP. So single. Then we're going to have your L equals 2p, double threaded screws. Then you're going to have your L equals 3p. So let's bring this down here. There we go. There we go. Okay. Now we have a coarse thread versus a fine thread. So the only difference is the pitch is smaller here. You notice that the pitch here is larger here, the pitch here is smaller. That's it. Yeah. Okay. So I mean I can write that down here. So we have, so we can have text coarse thread versus, so coarse threads versus fine thread. Okay, so coarse, so I'll just write here, control B. So we have coarse, oh wait, coarse threads have a larger pitch than fine threads. Okay, that's pretty much it. I don't think there's any more to this, to be honest. Okay, and then we can just include the picture of this where you have your coarse example and your fine example right here. All right, let's go here. The fine example. Then we have the right and left helical angle. So this is the way it tightens or it opens. So this, I think maybe we'll be asked to identify which angle it is. So the way we can do this is if you have this, okay. If you have this, let's show it here. So the quick way to doing this is just looking at which direction it's going in. So this is going here to here to here. I'm talking about this. We're just following this. Just following this. And this is right. Because it's going in this direction. Right? Yeah. And the other one will be going in this direction. Yeah. Okay. Yeah, that's how we can do it. Left angle, right angle. So I think you're just looking at just remembering these particular diagrams, I think should be enough. So let's bring this here, and I'm going to actually get rid of. Okay, let's just use our whole. Alright, cool. Okay, that's fine. Let's go to action, turn around, that's fine. Turnbuckle, yeah, that's okay. This is used, okay, thread profile here. We might be asked about why this is smaller and why this is larger. Okay, so thread profile. Okay, so P over 4, P over 2, P over 2, 3H over 8, 60 degrees, 30 degrees, P over 8. This is your pitch diameter, your diameter, your DR. DR is, hold on. DR. Where is it? Minor diameter? Yeah, I think that's minor diameter. Hold on. I think if we just go back here, I think it's DR, yeah. Okay. Yeah, dr equals d minus 10825p. This, in general, diagram is important to understand what's going on over here, but I don't think we'll be asked to label it, to be honest. But yeah, this diagram itself is important. Obviously, we don't need to know how to draw this, I believe. I don't think that will be an issue. It's just identifying what diameters we're going to use to solve the problems that we need to solve. So we have we're using isometric usually. We have coarse and fine. You have from their classifications. Now this is what we will be using, this part here. So M12 means, yeah, this is the one we're going to be using. So let's look at some definitions here. So for example, If I give you an example of M6 times I don't know, 0 point, no, not 0 point, yeah, 0.45. That means you're using diameter of 6 millimeters at P of 0.45 millimeter plus thread. Now I did make this number up, so that's just an example. I'll just give you an example here. Okay. Tolerance, there are several levels here. Tensile stress, AT, as effective area calculation of threaded rod to be used for stress calculation. Diameter of this unthreaded rod is the average of the pitch diameter and the minor diameter. So the diameter of this unthreaded rod that we use is the average. So this is the average, so dr. We use this calculation here. So we use this formula here. So we use, so we're given this force over area, and the area is just pi over 4 dp plus dr over 2 squared, which equals at equals pi dr squared over 4. Look at tables M. Okay. So we were given this in the example, in the question example. So this is an example. Determine the tensile load for a bolt of M30, assuming a safe tensile stress of 42 megapascals. So with this, you're given, we're trying to find the tensile load. So we're trying to find F. We're trying to find F here. So let's look at this over here. So let's look at this problem over here real quick. So we're trying to find, so this is this example. We're trying to find F, and that's this times AT. So F equals, let's look at this for a second. So we're told that F is equal to 30 megapascals, so 30 MPa times by pi dr squared over 4. Now we're using M30, so we're going to use M30. Okay, let's look at M30 here. So this is my M30, so I'm going to go here and just show you here. So this is my M30. Now what am I looking for in M30? I'm looking for my tensile area. So 561 millimeters squared. So I'm going to use that directly. I'm going to write here as F equals 30 times 10 to the power 6. 561 times, it's millimeters to the power squared, so that's also 10 to the power of minus 6. Okay. If you don't know, if you have MPa and by millimeters, it's just going to give you newtons, just as a reference. Okay, so we don't even need to write the times 10 to the power of 6. If you know this correlation, then you're fine. Okay, so 30 times 561, what you get is, oh wait, why do we do 30? Oh, it's 42. My bad, I just looked at that. So this will be 42. This will also be 42. My bad, guys. 42, 42, this cancels with this. So you're left with 42 times by 561. That's equivalent to 23562 newtons. So 23562 newtons. 23.6 kilonewtons. Okay. All right. Threading profiles. So we have, for power screws, we use a 29 degrees. For general use, we use 60 degrees. Okay. I think we can also mention this. Let's use our text option, and it's right here. So threaded profiles. Industrial use is 28 degrees, and Alright, I'll write power. You know what? I'll write power, aka power screws. And you know what I'll do here? I'll just go here. Here we go. Power screws and machine tool threads. So yeah, machine tool threads. Okay, 28%, 28. Okay, here we go. It's not machine tool threads. Let's move this down here. Or actually, here you go. Let's move it down here now. Okay, and this is not percent, this is degrees. I think it's option shift 8 or shift J. Option shift J. No, option shift 8. Yeah, there we go. 28 degrees and 60 degrees for general use. So for general use, use 60 degrees. And what I'll do here again is I'll bring this here. There we go. Hey, what's the issue now? Let's move this down here. Yeah, okay, that's fine. Okay, and let's just include this picture, quick picture here. Control V, and let's make it a bit smaller here. Bring this to the side, 29 degrees here. And the other one is general use. So, okay, and this over here, general use. All right. Okay. All right. Okay. Let's go over the rest. Let me go back to my default mode. Okay. So now we have hexagonal bolt heads. Okay, hexagonal bolt. Hexagonal bolt. Note the washer face, the fillet under the head, the start of threads, and the chamfer on both sides. Both lengths are always measured underneath the head. Now, because this is in bold, this might be asked, right? So we need to remember this. So for hexagonal bolts, so let's write this here. Hold on, let me see. There we go. Okay, let's add something here. Let's change the color to black. So hexagonal head bolt, and all the lengths are always measured underneath the head. Okay, that's fine. The fillet, third thread, see over both sides. No, the washer face, the fillet under the washer head, the third thread. Okay, are we just saying note the fillet, or? Okay, I think this is important here. The both lengths. Okay. Then you have your different typical cap screw heads. You have Philister head, flat head, hexagonal socket head. Okay, these are more, I think, self-explanatory. Types of head used on machine screws. So you have your round head, flat head, Philister head. Is this the same thing? Philister head? I think it is. Okay. Binding head, oval head, hex. Will we be asked to identify these? I'm not sure. If in the case we are, then I think we should just quickly write them down. So let's go here and write. So this is my round head. So I'm gonna write over here round head. All right, cool. Now quick fire. Let's get all of them first. Quick fire. This is over here. Quick fire. Let's get this one over here. Alright. Then we're gonna have it here. Okay, oval head. So I mean, they're not that similar, so I think we'll be able to make it out, to be honest, if we want to know the difference between some of them. So I don't think that's an issue. Okay, so let's just write it here. So this is supposed to be a flat head. This is supposed to be a Philister head. What happened? Let's open it again. That's weird. Let's go back down. Oh, hold on. What happened? Okay, so what we can do is we can just go on and just bang. Let's put it here. Let's bring this down here. Okay. I think that's pretty much it. Okay. Hexagonal nut. You have ignore. End view, general, washer, regular face, regular nut, chamfered on both sides, jam nut with washer face, jam nut chamfer on both sides. Now I do think we will be asked to draw one of these things, so it is a good practice to practice drawing these nuts. Okay, so because I think the professor did draw one of these before, if I'm not wrong. Yeah, he did. So let me just show you the other. Yeah, he drew this on the board. He drew this. So this is just for reference. This is what he drew. Okay. We got your head and key, your Allen key, and then you have your heads. Now I also don't think we'll be asked about this, but if we'll be asked, we'll probably just be matching it. So I don't think, again, this is like something very, very difficult. This is just remembering, rote learning on which one goes where. And it's also in the name. So if you look here, hexagonal shape goes to hexagonal. Which one? Slotted, one line. Cross slot, 2 lines. Positive driv, that's a slotted line with a weird star here. Security T, dot in the middle. And then torques. So that's the odd one out there. Okay. Types of thread fasteners. You have your bolt nut, cap screw, and stud. Okay, so they're all important. So bolt and nut, cap screw, and stud. Okay, so let's right here, over here. Let's go over here. Types of threaded fasteners. You got bolt and nut, cap screw, stud. Okay. Stud has no heads and thread at both ends. Okay. So let's write here stud. It's supposed to have a clearance hole. So clearance hole of 15 to 20% larger than the bolt size to facilitate assembly and to clear any head fillet. Okay. A tapped hole which is drilled much smaller than the root reminder. Okay. Oh, a tapped hole. So this is tapped hole here as well. So let's mention that. Okay. Tapped hole which is drilled at the root of the thread. Okay. Alright, let's just add this part here. So this is a tapped hole. Alright, okay. Locking devices, so to assist assembly or to prevent loosening under severe vibration, or a thin lock nut may be jammed against an ordinary nut, a lock washer, or a lock nut such as shown here. So you have a castle nut and then a cotter pin. So we can use this to lock devices together. Okay, that's pretty good. So to lock devices, so locking devices, combination of a pin and a designated nut such as castle nut and cotter pin can be used to prevent loosening under vibration. Okay, cool. That works, and we can just show this mechanism here. Cool. Over here. Okay, nice. Okay. Grade marking to help you choose the right fastener for your project. Head marking or cap screws are your assurance that fastener you choose will do the job assigned to do. The Society of Automotive Engineers, American Society for Testing Materials, so ASTM, and Industrial Fastening Institute have established specific ranges of hardness and tensile strength for each grade fasteners. There are certain applications which engineers are determined are appropriate for the various grades. Okay. Now these grades don't make sense to me on the numbers because look, you have 2. I don't see anything on it, and then you have 1 to 3. That's grade 5. 1 2 3 4. That's grade 6. 1 3 4 5. That's 7. 1 2 3 4 5 6. 1 2 3 4 5 6. That's 8. Okay, 5.8, 8. So okay, so the ones that we need to know are 2 and 8.2. The rest are just 1 2 3. Add 2 there. 1 2 3 4. Add 2 again. Add 2 again. Add 2 again. So the one we need to know is this one here. We need to know this one, and we need to know this one here. The rest we can wrote them, so this is fine. Okay, so this is your let's add a title here. This is common cap screw grade markings. Okay, so let me expand this. There we go. All right, Control B. Okay, there we go. Okay, let's move this to the side. Move this to the side. There we go. Okay. No marks used for. Okay, so now we need to know what they're used for as well. Okay, so small engine, 6 rating lines, automotive needs other than high tensile required. Okay, so maybe let's just write here. So this is used for. Let's use caption. So use for wood and general hardware. So okay, grade 8 and above. So let's write. Oh no, actually this is 8.2. So let's just write. So okay, actually I'll just include 8. Hold on. 4. Let's just add 8 as well. So grade 8, and let's write here. Automotive needs and other applications with a high tensile strength. Applications. Okay, so that's grade 8. And let's add grade 5 as well. Grade 5. So grade 5 over here. All right. So grade 5 is 3 rating lines. We have use for small engines. So use for engine repair. Used for small engine repair. Small engine repair. Okay, I'm just gonna say and automotive needs. Okay. That is engine with the E. Alright, cool. Now we're part D now. Now the mechanics of power screws. Power screw applications, where we see power screws, jackals for cars, material testing machine, machine tools, power screw type. So we have 1, 2, 3. Load distribution, this is not relevant. This is not relevant. This is not relevant. No, 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 no. This self-locking is important. And that's part E. Okay, so from this, all we need is where it's used. So we're just gonna add here part, this is what, part D. Yeah, so we'll add it here for caption to header 2. Part D, part D. Okay. And then all we're gonna do is where you have seen power screws. So power screws, change this to body, power screws, jacks for cars, material testing machines, and machine tools. Okay, this is where power screws have been used. Okay, anything else? We also know it's used. Okay, now we need to know the power screw types. There are 3 types. So what we can do is here we can do something like this. We can write types are square, acme, buttress. Okay, now with this we're gonna write strongest, no radial load, hard to manufacture. Okay, then we have your 29 29 angle. Oh, why is it bold? Okay, then we have easy to manufacture and common. No, this is loading by bi-directional loading, bi-directional load. Okay, buttress, great no. Great strength and only unidirectional loading. Okay, so what we're gonna do now, we're gonna do it one by one. So we're just gonna do this square. So this is square, this is acme, this is acme, and this is buttress. Okay, so gonna quickly just write stuff on top. So let's just write this is square, square, acme. I got your buttress. All right. Okay, load distribution. No, 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 none of this. No, no, no. This is just the force we'll get, a torque we'll get. Okay, cool. For lowering the load, just add it. This is okay. Now this is what we're interested with, is that self-locking and back driving. So self-locking is when the screw cannot turn from load F, load P. Back driving is when the screw can be turned from load P. So for self-locking, you need this more than L. So basically you need this to be positive. And for, if you don't want a self-locking, this needs to be less than L, so this will be negative. Okay? All right. Let's write that down here as well. So we have for self-locking. Okay, I hope that was saved. If not, then hold on. Yeah, reopen. reopen, please, and okay, still has it. Cool. All right, let's add over here self locking and back driving. So this is when you have self locking. Self locking is when you have screw cannot turn from load P, and back driving is when it can be turned. So screw can be turned from load P. Then we just have your diagram here. Let me just write it here again. Okay. And we have your for self-locking, so this diagram here. See if I can add it here. If I think I can. If I just move this to the side, move this to the side, move this to the side here. Yeah, okay. I just have to make this a bit smaller and done. Self-locking. Okay. Part E, bolted joint stiffness. So we have during bolt preload, bolt is stretched. Members and grip are compressed. When external load P is applied, bolt stretches further. Members and grip uncompress some. Okay. Bolt stiffness. Axially loaded rod, partly threaded and partly unthreaded. So partly threaded and partly unthreaded. Consider each portion as a string combined as two springs in series. So 1 over K plus 1 over K. Okay. This is from before. K equals EA over L. So your bolted stiffness will just, like I said, 1 over K equals 1 over K1 plus K2. Okay, so this is something that we haven't seen already. Procedure to find bolt stiffness. So bolt diameter, washer thickness, nut height. Okay, so we have your threaded length, a fastener length, because we weren't asked this in the quiz, or yeah, so I don't think this is something that's going to come, to be honest. So fasteners in shear, so this was there, I believe, for our tutorial. So this is more calculations now than understanding the concept of threads. So single shear when V equals F, then this is V equals F over 2, right? This next one for double shear. So single shear V over A, then V over 2A because F over 2. Now this is what we need to have, design consideration. So we need to have design consideration. So if you want to have protection sleeve, dowel joints, so two things, protection shield and dowel joints. Okay, so let's go to the shear part here now. So you can have shear, so single shear, so let's go here and write for single shear, so single shear, you have V equals F, you have V equals F. For double shear, you will have that V equals F over 2. Now with this, what you can get is over here that at the very end, you'll get your tau average. So I'll write this out now. So you get your tau average for this. Tau AVG is V over A, which is F over A. For this one, you'll have tau average as V over A. So F over 2 over A, which is F over 2A. Okay. Single shear versus double shear. The design consideration, when you have single shear, you want to put a protection sleeve on it. So let's put here, so for single shear, add a protection sleeve. So something like this, and we just show this. this part here. Okay, so here we go. Production save. Dowel joints. It is not good. Considered good practice to use bolts or screws and shear to locate and support precision machine parts under shear loads. So we use dowels. So dowels need both clearances. At best, 2 out of 4 will bear out of all the loads. Dowels support shear but not tensile load. Both support tensile load but not shear. This looks important, so let's write this down. So this is for dowels. Support shear but not tensile loads. Bolts support tensile loads but not shear. Okay. With this, we will add. No, I think that's it. I think that's it for. It also, okay. So let's add here. Good practice to use dowels. Okay. Okay, so let's add this 1 dot, 2 dot. Okay, done. Part G, good practice. So good practices are what? We have high eccentricity, so there's, if not, it's away from the center line, you want low eccentricity. So these things here are what we're after. So I'm just going to show this side by side. So I'm just going to write here. This is for eccentricity of the bolt. Okay, then we need high eccentricity between the force. So we apply the force here. So a low eccentricity of the force induce a low additional low inside the bolt. So high eccentricity, you're further away. If the force is applied further away from the bolt, then it can break more easily. So over here, bam. This over here, and I'm just going to let's see if I can. There we go. Yep. And this is for the force, so of the force. Okay. Introduction level of the force. If the force is introduced near the bolt head plane, that's bad. If you wanted to introduce it near the joint plane, so this is the joint plane, and that would further reduce the load on the bolt itself. Okay, that's good. So now we add here. So this is level of the force. Diameter of the support, this is a weak diameter, you want a large diameter. Okay, cool, that makes sense. So I can flex if it is flexing. Okay. Diameter of the support. Larger diameter, better. Okay. Force near joint plane, better. Extended force, low, better. Extended bolt, low, better. Okay. Thickness of the support, we need a sufficient thickness, so more thickness is good. So let's go here. Let's add it. Let's add it here actually. Will it fit here? Oh, actually it might. Okay, cool. If I can shift everything, hold on. If I can, yeah, I can do this. Okay. There, and if I, yeah, there we go. This right here. Sufficient thickness. Better. Okay. Minimum support, comfortable support. Okay, external supporting force must be bigger than the minimum value, so the maximum pressure remain lower than the critical pressure of the least resistant material. So I'm guessing if the force is applied here, you want it to have a small, more support so it can withstand. Okay, so it doesn't damage itself. Okay, that makes sense. Okay, so let's add it here. So over here, what would be the word? Let's see if I can. There we go. Okay, make this up and make this up. Actually, let's write it here. Yeah, that makes sense. And let's write this one here. Let's write this one. That's fine. Let's write this one here. Okay. Now with this, we want the supporting surface to be comfortable. So we need to write that supporting surface needs to support better. No, needs support more. Okay. Eccentricity of force, important eccentricity, minimum eccentricity. Okay, number of bolts, layout, location of bolts. Okay, okay. So I'll just have a couple more. Let's add them. So eccentricity of the force. Again, we want them to be as close as possible. Okay, so instead of that, I'm just going to just get the slides, paste them here. So this is obviously you could be asked about any one of these. So number of bolts, we don't want 4 bolts. So click out the redundant bolts. Layout, so free assembly, guided assemblies. So always avoid attachments of the belts. Okay, that makes sense. Always avoid a detachment of the assembly. Okay, so these are just good practices that we should know. It might be asked like very quickly. Oh, if the question was, okay, how do I make this better? For example, what's the reason? You will say, okay, it's a minimum support. You want to add a bit more support so it doesn't the surface, the external surface, does not shear away. Okay, something like that. Okay, so location of bolts, we want to make it so that they are with the force. So all right, let's mention it here. So with this, so ensure the bolt is in the same direction as the applied load to make sure no shear risk. Okay. All right, number of bolts, yeah, as many as possible. Not as possible, as many as required, you know, to make it stable. So as many as it requires to make it stable. So as many as it takes for structure to be stable. Location bolts, okay, this just makes sense. If okay, don't put it right next to it. So as in if you put it right on top, it'll be hard to remove and all. Okay, surface finishing and wide ranging. So instead of this, they added washers. Okay, cool. So let's add washers to reduce shear. So adding washers to reduce. So this is to reduce deformation. Add washers between the two surfaces and the nut. Okay. Okay. All right. Okay. I think that's it, and I'll see you guys later.